better understand the benefits of SequenceL, we'll start with an overview of just what this multi-core programming problem is. We have all noticed that our software doesn't always seem to run faster after upgrading to a newer computer. This is because, beginning around 2004, chip designers hit a technological wall and could no longer increase the clock speeds of their processors. So instead, they began to add more cores to their CPUs. This placed the burden of performance squarely on the shoulders of software application developers and their ability to write parallel code. Many people tend to assume the operating system automagically enables their application software to make use of all the cores in their modern multi-core computer, while others think virtualization technology deals with the multi-core problem. Unfortunately, it is not that easy. To better understand this industry challenge and the breakthrough approach SequenceL uses to solve it, we will turn to an analogy. Let's say I'm a contractor that moves huge boulders. I run a crane for each job and it's working great and my customers are happy. Next project, the crane rental guy shows up with two smaller cranes. He explains that combined, they can lift a little more than the big crane. But I remind him I only have one boulder to move. He tells me all you have to do is split the boulder in two. So I have no choice and I hire a mason to find fissures, split it, etc. A year later, the crane rental guy shows up with four smaller cranes. Again, he states the combined lifting capacity of these four is greater than the previous two. But now I have to split the boulder in four. So I hire more masons, I spend more time splitting the boulder. And of course this keeps getting worse. Next time the crane guy shows up with 8 smaller cranes. And now I have to split it into 8 smaller pieces. And next year it could be 32, 64, or 128. I now wonder if I'm in the boulder moving business or the boulder splitting business. This is analogous to the rapidly increasing number of cores present in today's computers. It has reached the point where developers spend the bulk of their time breaking up software instead of writing new features. Why is this so critical? Looking at Amdahl's law, the implications become readily apparent. For example, many programmers would be satisfied if they parallelize half of their code. However, the reality is it can never run more than 2 times faster, no matter how many cores it is run on. Even parallelizing 90% of an application maxes out at just 10 cores, so it is wasting so much of the power of today's high core count servers. Humans just don't write large-scale parallel code well, so a better automated approach is required. The SequenceL approach. Think of the SequenceL functional language and compiler as Marvin the Martian's ray gun from Looney Tunes cartoons. The auto-parallelizing compiler turns the boulder into a pile of sand. This reveals all of the parallelizations which occur naturally in the code. SequenceL is disruptive technology. If you look at the history of computing, it is clear the industry is overdue for its next move up in abstraction to deal with the complexity of multi-core systems. We've been essentially using the same tools with band-aids here and there since 1980, even though multi-core processors became mainstream in 2004. Also worth noting here is that each of these steps was met with resistance until ultimately being widely adopted, if not declared obvious in hindsight. With SequenceL, the programmer focuses on the what instead of both the what and the how. The inventors of SequenceL wisely chose to compile to industry standard parallel C++ instead of directly to machine code. This leverages programmer familiarity, high performance, wide platform support, and available frameworks and tools. This higher level of abstraction also means that hardware architectures and capabilities do not need to be known up front. You even get runtime control over the number and type of cores to execute on, which also makes it great for benchmarking target hardware platforms. SequenceL is a complete solution, including IDE plugins, debugger, interpreter, the auto-parallelizing compiler, and a runtime environment. It is the right tool for the job, designed to work in concert with C++ to quickly and easily solve complex problems. The decision to output parallel C++ also provides an easy incremental way to modernize software. It makes it possible to refactor just a portion of an existing program to SequenceL, at which point it can be compiled and the parallel C++ linked back into the remainder of the program. Let's see just how easy it can be to use SequenceL to write a program and run it across as many cores as you wish.
One of the key features of SequenceL is that developers are able to write relatively simple code which is capable of automatically taking full advantage of all the cores on multi-core systems. But more than that, the developer is able to specify the number of cores to use at runtime. Here we are seeing the writing of a simple program in SequenceL, which naively finds how many primes are below a given input integer. Something important to notice is that the C++ driver defines the variable cores, which is read off the command line. This variable is then used to inform the SequenceL runtime how many cores to use. In traditional parallel development, a developer must choose the number of cores they would like their program to take advantage of and program directly for that. With SequenceL, the developer can, once the code is written, experiment with different core counts to find the optimal number, factoring in the overhead of things like hyperthreading and operating system interference. Once the program is compiled, we can run the program, experimenting with various core counts while watching the Windows Performance Monitor to see how the program makes use of this computer's processor. This computer has an Intel i7, which has 4 physical cores, hyperthreaded to 8. As we increase the number of cores, the program gains a nearly linear speedup, going from about 14 seconds on one core, to about 7 seconds on 2, and to about 3.5 seconds on 4. The speedup appears to taper off a bit once we start using all the hyper-threaded cores. Also, if we don't want to specify the number of cores to use, we can pass 0 as a core count, which instructs the runtime to detect the maximum number of cores and run on all of them. One more thing you'll notice is that we did not have to sacrifice readability to gain this multi-core performance. In fact, the SequenceL code is very close to the mathematical definition of prime.
Returning to Amdahl's law, this chart shows the scaling performance of some customer programs that are now part of our test suite. Some perform better than others due to the nature of the algorithms, but the key is these are written very much like their mathematical representation, and they self-parallelize to run across as many cores as they can use in the system, whether that is 4, 10, 100, or thousands. This also means SequenceL programs are a good test of the capability of modern high core count systems.